Look at a clock for a moment. It seems like the most ordinary thing in the world. The second hand moves. Tick, tick. Each movement feels like proof that time is flowing forward. Seconds turn into minutes, minutes turn into hours, and before you notice it, an entire day has passed. This experience feels so natural that we rarely question it. Time moves forward. The past is gone. The future hasn't happened yet. The present is the only moment that truly exists. At least that is how it appears. But physics has a strange habit of questioning things that feel obvious. Again and again in science, the universe turns out to be very different from how human intuition expects it to be. For thousands of years, people believed time worked like a universal river. It flowed everywhere in exactly the same way. No matter where you were, no matter how fast you moved, time passed at the same steady rate for everyone. This idea felt perfectly reasonable. If two people each had a clock, those clocks should measure the same time. 1 minute for you should be 1 minute for me. But modern physics began to reveal something uncomfortable. That simple picture of time might be wrong. Before we go deeper into the physics, try imagining something unusual. Picture the entire history of the universe as if it were a long film reel from an old movie projector. The film contains thousands of frames. In one frame, a child is born. In another frame, that same person is celebrating a birthday years later. In another frame, they are old. When we watch a movie, the projector moves quickly through the frames one by one. Because of that movement, we see motion. We see change. Characters appear to move, speak, and live their lives, but the film itself doesn't move through time. Every frame already exists on the strip. The beginning of the story is there. The middle is there. The ending is there too. Nothing inside the film actually experiences time flowing. The only reason the story feels like it is unfolding is because the projector reveals the frames in a sequence. Now here is the uncomfortable question. What if the universe works more like that film reel than like a flowing river? What if every moment already exists? Your childhood, this exact moment, and events that will happen many years from now could all be part of a much larger structure. In everyday life, we imagine the present moment as something special. We feel like we are standing on a moving boundary between the past and the future. The past is behind us. The future is ahead of us, and the present keeps sliding forward like the tip of an arrow. But when physicists examine the laws that describe the universe, something surprising appears. Those laws rarely require a moving present. Most of the fundamental equations in physics describe relationships between events, not a flowing clock. They don't contain anything that says, this moment must come first, and that moment must come later. Instead, they describe a kind of structure, a pattern that includes time as another dimension of reality. If that sounds strange, it's because our brains are deeply wired to experience time as movement. Our memories stack up behind us. We remember yesterday. We don't remember tomorrow. That alone makes time feel like it is traveling in one direction. But feelings are not always reliable guides to how the universe actually works. There was a time when it felt obvious that the earth was standing still and the sun was moving around it. Our senses insisted on it. Every sunrise seemed to confirm it, and yet the deeper truth turned out to be very different. Time may be another example of this kind of illusion, something that feels obvious from the inside, but looks very different when we step back and examine the universe through the lens of physics. And this is where things start to become truly strange, because once scientists began examining time carefully, they discovered that it doesn't behave like a universal clock at all. In fact, different observers can experience completely different times, even while living in the same universe. Understanding that discovery would change physics forever. For a long time, scientists believed time was absolute. This idea came largely from the work of Isaac Newton, who imagined time as something universal and constant. In his view, time flowed evenly everywhere in the universe, like a perfectly steady cosmic clock. No matter where you were or how you moved, 1 second would always be exactly 1 second. This seemed completely reasonable. If two people each had a clock and compared them, Both clocks should show the same passage of time. Time in this picture was independent of everything else. Space was one thing, time was another, and both behaved in predictable ways. For more than 2 centuries, this view worked extremely well. It allowed scientists to predict the motion of planets, calculate the paths of cannonballs, and understand many everyday physical phenomena. But toward the end of the 19th century, cracks began to appear in this picture. Experiments studying light revealed something deeply puzzling. No matter how fast an observer moved, the speed of light always appeared to be exactly the same. This result seemed impossible under the old understanding of time and space. Imagine driving in a car and throwing a ball forward. To someone standing on the road, the ball moves faster than it does relative to you inside the car. Speeds normally add together like that. Light refused to behave this way. No matter how fast someone moved toward or away from a beam of light, measurements always showed the same speed. This result forced physicists to reconsider their assumptions about time itself. In 1905, Albert Einstein proposed a radical solution while developing what is now called the special relativity theory. Instead of assuming time was universal, Einstein suggested something far more surprising. Time could stretch and shrink depending on motion. If an object moves extremely fast, close to the speed of light, time for that object slows down compared to someone standing still. This effect is known as time dilation. At first, this sounds impossible. After all, how can time itself slow down? Clocks may break or malfunction, but time should be independent of the device measuring it. Yet in relativity, it is not the clock that changes. Time itself behaves differently. Imagine 2 identical twins. One stays on Earth while the other travels on a spacecraft moving extremely fast through space. When the traveling twin eventually returns, less time has passed for them than for the twin who remained on Earth. This scenario is often called the twin paradox, and while it sounds like science fiction, the underlying physics has been tested many times with precise clocks and high-speed particles. The results always confirm the same strange conclusion. Motion affects time. Gravity affects time as well. Einstein later expanded his theory into general relativity, showing that strong gravitational fields can slow time down. Near massive objects like planets or stars, time passes slightly more slowly compared with regions of weaker gravity. Even on Earth, this effect is measurable. Atomic clocks placed at higher altitudes tick slightly faster than clocks at sea level, because gravity is weaker farther from the planet's center. These differences are tiny in everyday life, but they become extremely important for modern technology. The satellites that make the global positioning system work must constantly correct for these relativistic effects. Without those corrections, GPS navigation would accumulate errors of several kilometers each day. All of this leads to an unavoidable conclusion. There is no single universal time shared by everyone in the universe. Different observers can experience time at different rates depending on their motion and their position in a gravitational field. What we once thought of as a single, steady cosmic clock turns out to be something far more flexible and strange. Time is not separate from the rest of reality. It is deeply connected to space, motion, and gravity in ways that completely reshape how we understand the universe. To understand just how strange time really is, consider a simple situation that involves a train, 2 flashes of lightning, and 2 observers who disagree about reality. Imagine a very long train moving down a track at an extremely high speed. In the middle of the train sits a passenger. At the same moment, 2 lightning bolts strike the train, one at the front and one at the back. Now imagine a second observer standing on the ground beside the track, exactly as the lightning strikes. From the perspective of the observer on the ground, the situation appears straightforward. The lightning bolts hit the front and the back of the train at the same time. Because the observer is standing exactly halfway between the 2 strike points, the flashes of light travel equal distances toward them. The light from both strikes reaches their eyes simultaneously. So the observer on the ground concludes something simple. The lightning strikes happened at the same moment. But now consider the passenger sitting in the middle of the moving train. At the instant the lightning strikes occur, the train is moving forward along the track. Because the passenger is moving toward the front of the train, they are moving toward the light coming from the front strike. At the same time, they are moving away from the light coming from the back strike. Light travels at a constant speed. Because the passenger is moving toward one flash and away from the other, the light from the front strike reaches them sooner than the light from the back strike. When the passenger sees the flashes, they arrive at different times. The front flash appears first. The back flash appears later. From the passenger's perspective, the only reasonable conclusion is that the lightning bolt at the front must have struck earlier than the one at the back. Here is the remarkable part. Both observers are correct. Neither observer made a mistake. Neither one measured anything incorrectly. The difference arises because they are moving relative to one another. This situation demonstrates one of the most surprising consequences of the theory developed by Albert Einstein. Events that appear simultaneous to one observer may not be simultaneous to another. This idea is known as the relativity of simultaneity, and it completely changes how we think about time. In everyday life, simultaneity feels obvious. If two fireworks explode at the same moment, everyone nearby would normally agree they happened at the same time. But when objects move at extremely high speeds, close to the speed of light, this agreement disappears. Different observers construct different versions of now. The idea of a single universal present moment, the sense that the entire universe shares the same instant of time, begins to fall apart. Instead, each observer carries their own slice of time, depending on how they move through space. This is difficult for the human mind to accept because our brains evolved in a world where speeds are very small compared with the speed of light. Under ordinary conditions, the differences are so tiny that they go completely unnoticed. But when physics explores the universe at its most fundamental level, these differences become unavoidable. The conclusion is unsettling. If observers moving relative to one another cannot agree on which events happened at the same time, then the idea of a single shared present moment may not exist at all. What one observer calls now might belong to another observer's past or future. Time, in this deeper sense, becomes something far less universal and far more dependent on perspective than we ever imagined. Once physicists realized that different observers could disagree about what events happen at the same time, a deeper question began to emerge. If there is no universal now, what does the universe actually look like? To understand the answer, physicists began thinking about time in a completely new way. Instead of imagining time as something that flows, they started treating it as another dimension of reality. We are already familiar with three dimensions of space. You can move left or right. You can move forward or backward. You can move up or down. Every object in the universe exists somewhere within these three spatial directions. Now imagine adding another dimension alongside them. That extra dimension is time. In modern physics, space and time are not separate things. They are woven together into a single structure known as spacetime. This idea was first recognized through the work of Albert Einstein and later clarified mathematically by the physicist Hermann Minkowski. Instead of thinking about where something is in space, physicists describe events using 4 coordinates, 3 for position in space and 1 for position in time. Your birth happened at a certain place in a certain moment in time. A star exploding millions of years ago happened somewhere else and at a different moment. Every event in the universe occupies its own location within this 4-dimensional structure. Once you imagine reality this way, something surprising becomes possible. The universe can be thought of as a complete 4-dimensional object. In this picture, time does not flow like a river. Instead, the entire history of the universe is part of a single structure that already exists. Physicists sometimes call this idea the block universe. In the block universe view, the past is not something that disappeared. The future is not something that has yet to be created. Both are simply different regions, Within the larger structure of space-time, imagine a very long road stretching across a landscape. A traveler walking along the road only sees the small section around them. The places behind them still exist, even though they are no longer visible. The places ahead also exist, even though the traveler has not reached them yet. From the traveler's perspective, the journey feels like movement through time. From a bird's eye view above the landscape, the entire road already exists at once. The block universe suggests that reality might work in a similar way. Every event, your childhood, this moment right now, and events that will happen far in the future, could all be part of the same four-dimensional structure. Nothing needs to come into existence moment by moment. Everything simply occupies its own location in space-time. This idea challenges one of our deepest intuitions. Human experience tells us that the present moment is special. It feels like the only part of time that is truly real. The past feels fixed and unreachable, while the future feels open and uncertain. But in the block universe picture, the present may not have any special status at all. Different observers moving through space-time can slice this four-dimensional structure in different ways. What counts as null for one observer may include events that another observer considers part of the future. The sense of a moving present might not be something built into the universe itself. It may simply be how conscious beings experience their path through space-time. Physics cannot yet say whether this picture is the final description of reality, but the mathematics of relativity strongly suggests that the universe behaves as though time is another dimension rather than a flowing substance. If that is true, then the passage of time may not be a fundamental feature of the cosmos. Instead, it may be something that emerges from how observers exist inside the structure of space-time itself. If the universe might be a four-dimensional structure where all moments exist, then a natural question appears. Why does time feel like it moves? Why do we experience one moment after another instead of perceiving the entire structure at once? The answer may have less to do with physics itself and more to do with how our minds work. Human experience is built on memory. You remember yesterday. You remember events from earlier today. But you do not remember tomorrow. This simple fact creates a powerful psychological effect. Because memories accumulate behind us, it feels as though we are moving forward through time. In reality, what we call the present might simply be the point where our brains are currently processing information. Think about reading a book. When you read page 50, you remember the pages that came before it. But you do not yet know what happens on page 80. The story appears to unfold gradually as you move through the pages. However, the entire story already exists inside the book. Page 1 and page 200 are printed at the same time. The narrative feels like it progresses only because the reader experiences it sequentially. Some physicists suspect our experience of time may work in a similar way. Conscious observers might move through the structure of space-time step by step, creating the sensation of a flowing present. But the deeper laws of physics themselves often do not care about the direction of time. Many of the fundamental equations describing nature work equally well if time runs forward or backward. The equations governing motion, electromagnetism, and even many aspects of quantum mechanics remain valid if the direction of time is reversed. Imagine watching a video of two billiard balls colliding on a table. If the video is played forward, the balls roll together, collide, and move apart. If the video is played backward, the motion still obeys the laws of physics. Nothing in the equations forbids that reversed version. Yet everyday experience tells us that time clearly has a direction. Glasses fall and shatter, but shattered pieces never spontaneously leap together to form a perfect glass again. To understand this difference, physicists study a concept called entropy. Entropy is often described as a measure of disorder. A neat arrangement of objects has low entropy. A scattered arrangement has high entropy. The laws of thermodynamics state that in an isolated system, entropy tends to increase over time. This principle creates what scientists call the arrow of time. When a glass falls from a table and breaks, the fragments scatter into many possible arrangements. There are vastly more ways for the pieces to exist in a disordered state than in the single highly organized state of an intact glass. Because disordered states are so much more probable, systems naturally evolve toward them. That statistical tendency gives time a direction in our everyday experience. We see processes where order turns into disorder, but we almost never see the reverse. However, this explanation raises another mystery. If entropy tends to increase, then the universe must have started in a very low entropy state long ago. Otherwise, the arrow of time would not exist. Why the early universe began in such a highly ordered condition remains one of the deepest unanswered questions in physics. So the sensation of time moving forward may arise from a combination of factors. Our brains store memories in one direction. Physical systems tend to move toward higher entropy. Together, these effects create the powerful impression that time flows from past to future. But the underlying laws that govern the universe may not include a preferred direction of time at all. If that is true, then the flow of time might not be a fundamental property of reality. It could instead be an emergent feature that appears when conscious observers and thermodynamic processes interact within the larger structure of space-time. To understand why time appears to move in one direction, physicists often look at ordinary events that happen around us every day. Consider something simple: an egg falling onto the floor. When the egg hits the ground, it breaks. The shell cracks, the yolk spreads, and the pieces scatter in different directions. Once this happens, we never see the reverse process. The liquid does not suddenly gather itself together, the shell pieces reconnect, and the egg jump back onto the table. Nothing in the fundamental laws of motion explicitly forbids that reverse sequence. The equations that describe the movement of atoms could, in principle, run backward just as easily as forward. If every atom in the broken egg somehow reversed its motion at exactly the right moment, the egg could reassemble itself. But in reality, this never happens. The reason has to do with probability and with a concept that lies at the heart of thermodynamics: entropy. Entropy can be understood as a measure of how many possible arrangements exist for a system. A highly ordered system has very few possible arrangements. A disordered system has vastly more. A whole egg sitting intact on a table represents a very special arrangement of atoms. The molecules inside it are organized in a precise way that keeps the shell together and the contents contained. When the egg breaks, the atoms can scatter in countless different patterns. There are unimaginably many ways for a broken egg to exist, but essentially only one way for the egg to remain perfectly whole. Because there are so many more disordered arrangements than ordered ones, physical systems naturally drift toward disorder. Not because the universe prefers chaos, but because disorder simply corresponds to far more possible configurations. This statistical tendency is summarized by the second law of thermodynamics, which states that the total entropy of an isolated system tends to increase over time. From this principle emerges something physicists call the arrow of time. The arrow of time is not a force pushing events forward. Instead, it is a description of how physical systems tend to evolve from states with fewer possibilities to states with many more possibilities. Imagine shuffling a deck of playing cards. A brand new deck begins in a very specific arrangement. After a few shuffles, the cards become mixed in a seemingly random order. The mixed state can occur in an enormous number of ways, while the original ordered state can occur in only one. The laws of motion governing the cards do not forbid them from returning to their original order. But the probability of that happening by chance is incredibly small. Because of this, we observe a clear direction in time. Ordered arrangements tend to become disordered ones. This same principle applies to melting ice, spreading perfume, burning wood, and countless other processes in the natural world. A cube of ice melts into water, but water rarely gathers itself spontaneously into a perfect cube of ice at room temperature. A drop of ink spreads through a glass of water, but it never naturally pulls itself back into a single drop. All these processes increase entropy. However, this explanation leads to a deeper mystery about the universe itself. If entropy naturally increases, then the early universe must have started in a state of extremely low entropy. Otherwise, there would be no direction for entropy to increase toward. The question then becomes, why did the universe begin in such a highly ordered state? Cosmology studies the early stages of the universe following the event known as the Big Bang. Observations suggest that the universe began in a remarkably smooth and organized condition. Matter and energy were distributed with extraordinary uniformity across vast distances. From that low entropy beginning, entropy has been increasing for billions of years as stars formed, galaxies evolved, and complex structures emerged. Yet physics still cannot fully explain why the universe started in that particular state. The arrow of time we experience may therefore be tied to the initial conditions of the cosmos itself. The direction from past to future might reflect the way entropy has been rising since the earliest moments of cosmic history. In this sense, the flow of time may not be a fundamental property written into the laws of nature. Instead, it could be a consequence of how the universe began and how probability guides the evolution of complex systems within it. Physicists often reach a point where the deeper they investigate reality, the less it resembles ordinary experience. One of the scientists who spoke most honestly about this strange situation was Richard Feynman. Feynman had a reputation for explaining difficult ideas with simple examples, but he was also careful not to pretend that physics had solved every mystery. He frequently reminded students that understanding the equations of nature does not necessarily mean we fully understand what those equations imply about reality. When discussing time, Feynman emphasized something subtle but important. Many of the fundamental laws of physics do not actually distinguish between past and future. Take the motion of objects, for example. Imagine recording a video of two billiard balls rolling across a table. They collide, change direction, and continue moving apart. If someone watches that video in reverse, the motion still appears physically possible. The balls approach one another, collide, and move away. Nothing in the laws of motion immediately reveals whether the video is playing forward or backward. The equations describing these motions work equally well in both directions of time. This symmetry appears in many areas of physics. The laws governing electricity and magnetism behave the same way. Even large parts of quantum mechanics have this time reversible property. Yet the world around us clearly does not behave symmetrically in time. When you drop a glass onto the floor, it shatters. But shattered pieces do not suddenly leap together to form an intact glass and jump back onto the table. When cream mixes into coffee, it spreads through the liquid. The mixture does not spontaneously separate back into cream and coffee again. These everyday observations give time a clear direction. Feynman pointed out that this difference between the reversible laws of physics and the irreversible events we observe is one of the deepest puzzles in science. To understand why this happens, it helps to imagine the behavior of atoms. Every object around you is made of enormous numbers of atoms moving in complicated ways. A glass cup contains trillions upon trillions of particles vibrating and interacting with each other. When the glass falls and breaks, those atoms scatter into many different configurations. Each piece can move in countless directions. Each fragment contains its own atoms moving randomly. For the glass to reassemble itself, every one of those atoms would need to reverse its motion in exactly the correct way at exactly the correct moment. The fragments would have to fly together with perfect precision, reconnecting every molecular bond. In principle, the laws of physics do not forbid such a process, but the probability is unimaginably small. The reason is connected to the enormous number of particles involved. Even a tiny object contains more atoms than humans can easily imagine. The number of possible arrangements of those atoms is so large that a disordered state becomes overwhelmingly more likely than an ordered one. Feynman liked to explain that this statistical behavior gives rise to what we experience as the direction of time. It is not that the laws of nature demand that time move forward. Instead, systems with huge numbers of particles almost always evolve toward the most probable states. Those states tend to be the ones that appear messy, mixed, or disorganized. From the perspective of human experience, these processes create a clear sense of before and after. The intact glass exists before it shatters. The mixed coffee exists after the cream spreads. But at the level of fundamental physics, the equations themselves remain indifferent to the direction of time. This realization leads to an uncomfortable conclusion. The arrow of time we experience may not come directly from the basic laws of the universe. Instead, it may arise from statistical behavior when large numbers of particles interact. Feynman believed that recognizing this distinction was important for scientific honesty. Physics can describe how systems behave and predict the probabilities of different outcomes. But explaining why the universe began in conditions that allow this arrow of time to exist is a deeper question. It is a question that scientists are still trying to answer. When physicists began exploring the microscopic world described by quantum mechanics, the concept of time became even more mysterious. Quantum theory describes nature at the scale of atoms and subatomic particles, and many of its predictions seem deeply counterintuitive. One of the strangest phenomena discovered in quantum physics is called quantum entanglement. Entanglement occurs when two particles interact in such a way that their properties become linked. After this connection forms, measuring one particle instantly determines the state of the other, even if the particles are separated by enormous distances. This behavior troubled many physicists when it was first proposed. In fact, Albert Einstein famously referred to it as spooky action at a distance. The idea seemed to suggest that information could travel faster than light, something that appears to conflict with the principles of relativity. Experiments performed over the past several decades have repeatedly confirmed that entanglement is real. When scientists measure entangled particles, the correlations between them appear instantly, regardless of how far apart they are. At first glance, this seems to challenge our normal understanding of cause and effect. In everyday life, causes happen before effects. A light switch must be flipped before the room becomes bright. A stone must be thrown before a window breaks. Entangled particles seem to blur that simple sequence. The outcome of one measurement appears connected to another measurement that might occur far away, and at nearly the same time. Physicists have worked hard to understand what this means without violating the speed limit set by the speed of light. Careful analysis shows that entanglement does not allow useful information to travel faster than light. However, it still reveals that the relationships between events in quantum physics are far more subtle than classical intuition suggests. Some researchers believe that this strange behavior hints at a deeper structure beneath spacetime itself. One possibility is that time may not be a fundamental ingredient of the universe. Instead, time might emerge from more basic relationships within quantum systems. To understand what this means, it helps to think about other properties that emerge from simpler components. Temperature is a familiar example. A single molecule does not have a temperature. Temperature only becomes meaningful when huge numbers of molecules move and interact together. In a similar way, some physicists suspect that time may arise only when many quantum processes combine to produce the large, scale world we observe. Several theoretical approaches explore this idea. In certain models of quantum gravity, time disappears from the most fundamental equations describing the universe. Instead of a flowing timeline, these equations describe relationships between quantum states. From this perspective, time might appear only when observers measure and compare those states. Another reason scientists take this possibility seriously is that two of the most successful theories in physics treat time very differently. General relativity describes gravity and the large-scale structure of spacetime, while quantum mechanics describes the behavior of particles at extremely small scales. Each theory has been tested with remarkable precision, yet they remain difficult to combine into a single consistent framework. When physicists attempt to unify these theories, the concept of time becomes one of the biggest obstacles. In some proposed equations describing quantum gravity, Time does not appear at all. The universe is described as a collection of relationships that exist simultaneously without a universal clock ticking in the background. If these ideas are correct, then time might not be a basic feature of reality. Instead, it could be something that emerges from deeper quantum processes, much like waves emerge from the motion of water molecules. This possibility remains speculative, and many questions remain unanswered. Scientists continue to debate whether time is fundamental or emergent. But the exploration of quantum physics has made one thing increasingly clear. The familiar sense of time passing from past to future may not be built into the universe at its deepest level. It could be a feature that appears only when complex systems like observers and measuring devices interact with the quantum world. Human beings find the nature of time difficult to understand, not because the mathematics is impossible, but because our brains were never designed to think about reality at this level. The human mind evolved to solve practical problems in a very specific environment. Early humans needed to recognize patterns, remember where food could be found, predict the behavior of animals, and avoid danger. To survive, the brain developed ways to organize events into a clear sequence. Something happens first, something else happens afterward. This simple structure of past, present, and future is extremely useful for everyday life. It allows us to plan, remember, and learn from experience. But the mental framework that helps us survive is not necessarily the same framework the universe uses to operate. Many ideas in modern physics feel strange for exactly this reason. Our intuition was built from experiences involving slow speeds, moderate temperatures, and objects of ordinary size. When we examine the universe at very large scales, extremely high speeds, or very small distances, those intuitions begin to break down. The concept of time is one of the clearest examples. In daily life, it feels obvious that there is a single present moment shared by everything in the universe. It feels natural to imagine the past as something that no longer exists and the future as something that has not yet been created. But the discoveries of scientists such as Albert Einstein show that this picture is incomplete. According to the theory of relativity, different observers moving relative to each other can disagree about the timing of events. Two people traveling in different ways through spacetime may not share the same definition of now. The idea that the present moment is not universal is extremely difficult for the human mind to grasp. Our perception insists that time flows uniformly and that everyone experiences the same moment together. Yet the structure of space-time suggests that reality may be organized differently. The same challenge appears when people first encounter the strange predictions of quantum mechanics. Particles behave like waves. Objects can exist in multiple possible states until they are measured. Events that seem separate may become deeply connected through entanglement. These ideas feel almost impossible to picture because our brains evolved in a world where such phenomena never appear directly in everyday experience. The physicist Richard Feynman once commented on this problem with characteristic honesty. He suggested that if someone believes they truly understand quantum mechanics in an intuitive sense, they are probably mistaken. The theory works extraordinarily well at predicting experimental results, yet its deeper meaning continues to challenge human imagination. Time may belong in the same category. The mathematics of relativity and thermodynamics can describe how time behaves in different circumstances. Physicists can calculate how clocks slow down near massive objects or how entropy increases in complex systems. But translating those equations into an intuitive picture of reality is much harder. Part of the difficulty comes from the fact that humans experience only a tiny portion of the universe's possible conditions. We move far slower than the speed of light. We experience gravity at only one particular strength. We observe events at scales where quantum effects are hidden inside enormous numbers of particles. Because of this limited perspective, the deeper structure of reality can appear almost alien when revealed through physics. The challenge for scientists is not only to discover accurate mathematical descriptions of the universe, but also to find ways of explaining those discoveries in language that human minds can understand. Even with the best explanations, some aspects of time may always remain counterintuitive. Our brains evolved to navigate a world of survival and daily experience, not to visualize the geometry of space-time or the probabilistic behavior of quantum particles. This gap between intuition and reality is not a failure of science. It is simply a reminder that the universe is far richer and more complex than the environments in which the human mind first evolved. Even after more than a century of scientific exploration, some of the deepest questions about time remain unanswered. Physicists have made extraordinary progress in describing how time behaves under various circumstances. Yet the fundamental nature of time is still a profound mystery. One of the first questions is whether time is truly fundamental, or if it emerges from more basic elements of the universe. In classical physics, time was treated as an ever-present backdrop, a continuous flow against which all events occurred. In relativity, time becomes intertwined with space, stretching and contracting depending on motion and gravity. In quantum mechanics, time sometimes seems to vanish entirely from the most fundamental equations, appearing only when measured indirectly. Reconciling these views remains one of the biggest challenges in modern physics. Another mystery concerns the beginning of the universe. Observations of the cosmos suggest that the universe started in a remarkably low entropy state. Entropy, a measure of disorder, has been increasing ever since, giving rise to the arrow of time that we experience. But why the universe began in such an extraordinarily ordered condition remains unknown. Was it a random fluctuation? Was there a deeper principle that set this initial state? The laws of physics as we know them do not provide a clear answer. The behavior of time near extreme objects like black holes introduces additional puzzles. According to general relativity, time slows dramatically in strong gravitational fields. Near the event horizon of a black hole, time almost stops relative to a distant observer. This means that events near the black hole could appear frozen to someone far away. But the interior of black holes and the fate of time inside them are still largely theoretical, especially since general relativity and quantum mechanics produce conflicting predictions in these extreme conditions. Understanding how time works in such environments may require a theory of quantum gravity, a framework that has yet to be fully developed. Time also challenges our understanding of cause and effect. In the quantum world, entangled particles behave in ways that seem to connect events instantaneously across vast distances. While no usable information travels faster than light, these correlations challenge the classical intuition that one event must strictly precede another. Some physicists speculate that time itself could be emergent, appearing only at scales large enough for these probabilistic quantum relationships to form the ordered, sequential reality we perceive. Philosophically, time forces us to question our place in the universe. If the block universe picture is correct, then the past, present, and future all exist simultaneously in space-time. The sense of a flowing present would be a product of consciousness moving along a particular trajectory through this structure. The flow of time might not be a property of the universe itself, but rather a feature of how observers experience it. This perspective transforms our understanding of reality, suggesting that what we call the future is already part of the cosmos, even if we have not yet perceived it. Despite all these puzzles, humans continue to search for answers. Experiments test the limits of relativity, probe the strange behaviors of quantum systems, and observe the early universe with increasing precision. Each discovery refines our understanding, but also often reveals new layers of complexity. Time remains one of the most profound enigmas in science. Its apparent flow may be a product of memory, probability, and perception, rather than an absolute feature of reality. Understanding time challenges not just our physics, but our intuition, forcing us to confront a universe far stranger and more intricate than the one our ancestors imagined. In this sense, time is not only a scientific puzzle, it is a window into the deep structure of existence itself.